Hi everyone. In this video, we will explore the NTO architecture, that is the heart of QNX real-time operating system. So by the end of this video, you will understand how QNX achieves high reliability, modularity, and real-time performance through its unique microkernel-based design. I'm Dr. Dhanalakshmi, Professor, ECE Department, SRM Institute of Science and Technology, Katangutur campus. Before going to talk about QNX, let's know the need for RTOS, that is real-time operating system. So for that, we have compared here the Windows or Linux-based OS and also the RTOS. Yes. Let's imagine a self-driving car controlled by an OS. It continuously receives input from different sensors like camera, LiDAR, radar, and ultrasonic sensors. Let's have an assumption that if one of these sensors, let's say a camera sensor, experiences a delay in sending data, even by a few milliseconds, the object detection or the lane detection system might fail. That small delay can cause the car to misguide the distance or miss a pedestrian, leading to a dangerous accident. Yes, so that's why we need RTOS, which means we need a deterministic and predictable timing for our OS. Yes. So here, when you talk about Windows or Linux-based, general purpose OS, they are not deterministic and there no guaranteed timing for them. Whereas coming to real-time operating system, they are highly deterministic and they guarantee their timing deadlines. When coming for scheduling, here a fairness and time sharing based scheduling is there. So which leads to delay the higher priority task. Whereas when you come to RTOS, here it's a priority based preemptive scheduling, which means the highest priority runs first. That is, let's take if a new process with a higher priority is arriving while a lower priority process is running, the CPU immediately preempts, that is, interprets the running process and gives control to the higher priority one. That's called as preemptive scheduling. It is highly needed for real-time applications. Coming to the latency, here in the case of general purpose, they have high latency and unpredictable latency. Whereas coming to real-time operating systems, they have a very low and predictable latency. Talking about memory management, for the general purpose OS, they have dynamic memory and also have virtual memories, and which means you have paging there, swapping is all possible there. Whereas coming to the RTOS, it's all with static memory allocation and there is no paging and swapping, which means that memory is typically allocated at compile time only, which means static, rather than dynamically during their runtime. Right? That's called a static memory allocation. Coming to the resources usage, they are very heavy. They requires more RAM and CPU storage. Whereas coming to RTOS, they are lightweight and they have a small footprint of in the range of KB to MB. And coming to the applications, here it is used in PCs, servers, and mobile devices, whereas RTOS is used in real-time and safety critical systems. So in one line, if you wanted to compare both, I could say Windows or Linux is a powerful multitasking best effort, but it's not real time. When coming to RTOS, they are highly predictable, highly deterministic, and deadline driven. So we prefer RTOS for the real-time applications. Coming to the main components of an operating system, we have the kernel, and kernel is nothing but the core part of the OS. It manages hardware and system resources. Coming to the process management, it creates and schedules and terminates the process. It handles multitasking and CPU allocations. Memory management, It manages RAM allocation and deallocation. It handles virtual memory, paging, and segmentation in the case of general purpose OS. And file system management organizes and controls data storage. It manages files, directories, permissions, all is taken care by it. Device management, it controls and communicates with IO devices, users, device drivers as well. Coming to the sixth important component, input-output system management. It handles input-output operations and it provides buffer, cache, and spooling. Security aspect, it controls the access rights. It ensures data integrity and user authentication. And also coming to user interface, GUI and CLI, which means command line interface. And the networking side, it manages the communication between the systems. It uses network protocols. And finally, system utilities, tools for system maintenance, example, task manager, disk cleanup, and backup tools. So, come particularly talking about monolithic kernels and QNX burst kernel architecture. So here we could see that the monolithic kernel is almost the entire operating system that is running inside the kernel space as a single large program. It contains scheduler, memory management, file system, device drivers, system services, etc. It contains all within it. So everything operates inside one big memory space with full privileges. So what will happen if any one of these components, example, say device drivers, fails or crashes? The entire system may crash because they all share the same kernel memory. Yes. In contrast, coming to the QNX microkernel, it follows a very much modular design. Only the essential services such as scheduler, interrupt handling, and IPC, which means interprocess communication, they alone run inside the kernel, and everything else like device driver, file system, network stack, character drivers, GUI components, bus manager, system daemons, it all runs as a separate user space process. Separate process. These components communicate with the microkernel through message passing. So by this, you could say that QNX design is highly fault tolerant and isolated. I have made the difference here very particularly about the monolithic. Let's talk about Linux and here QNX based microkernel. So as I said, the entire OS all runs in the same kernel space as a big program there. But here scheduler, IPC and interrupts run in the kernel and others run in the user space. So here you need a large kernel size in terms of MBs. Here you have it's required very small kernel size in the order of KBs. So here lower fault isolation, a bug in the driver can crash the entire whole system because it's all inside the same big program. Here, when you have a device driver being failed, that alone will not work, whereas the remaining other process keeps on running, not the entire OS disturbed. And here it's fast, performance is fast due to direct calls, system calls, and no IPC overhead. Maybe here there's a slight overhead due to message pausing here and IPC between the services. Coming to the security, the main path which we look for applications, real-time applications or security. Here less secure because they have a large kernel attack space. Here it's highly secure because they have minimal kernel reduces the vulnerabilities. Minimum kernel space. The modularity is not that good here. Components are tightly integrated. Here it's highly modular services can be restarted, updated, all separately. Scalability. Here it's difficult to scale for deeply embedded or safety critical systems. Here it's highly scalable. You can use it aerospace, automobile, medical, what so not. Use cases, PCs, servers, mobile phones, where we have Ubuntu and Android. And coming to the applications here, automobile, avionics, medical devices, where all you need a real-time and mission critical systems, we go with QNX. Coming to the NTO architecture, yes, I was talking about the microkernel and the remaining process. So let's talk about this microkernel. I was telling you the scheduler and IPC all inside it, right? What is proc NTO? It means process plus NTO. NTO is nothing but neutrino, the name given by the QNX. So here, proc NTO, I could say it's a combination of microkernel plus process manager. So these two put together is called proc NTO, which means process plus NTO. And what is the purpose of this microkernel is, and how it could be reached by using function calls or kernel calls. And it handles all types of threads and IPCs. And it handles low-level hardware abstraction, manages scheduling, priority-based or fully preemptive, it decides. And it offers synchronization primitives like mutex or conditional variable or pulses. And coming to the next point, manages IPC at the lowest level, either message passing, signals, or pulses. And it could also handle the interrupt management, attaching the ISR safely to the user process. Coming to the process manager, it's not inside the microkernel. Yeah, it's first separate out of the microkernel. So all the communications within it happens through IPC messages. The process manager, that is the proc we call, it's a user space server that manages process creation, thread creation, memory management, path name resolution, executable loading, resource managers, drivers, etc. And it creates and destroys the process and threads depending on the application. It manages virtual memory, address space, mapping, and protection, implements the path name resolution, and it provides resource manager framework for device drivers. So I could say that the process managers are tightly bound, sharing the same address space, but operate differently. And note that they are the first process in the system, and we call it by process ID 1. That is, we call by PID, process ID. And this is process ID 1. So one main point is that NTO architecture, we call it as proc NTO, process plus NTO. It contains microkernel and process manager put together is called proc NTO, that is process plus NTO. QNX or task architecture, you have some trade-offs there. Yes, in talking about the benefits, as I told you, it's resilience and reliability, because you can isolate the fault. Fault isolation is there. User space driver services can crash without affecting the kernel. And the components can be restarted without rebooting the entire overall OS. And it's easy for configuration and reconfiguration. You can add, remove, update services at runtime. And it's highly modular in structure. It's easy for debugging, which means drivers are regular process and no kernel panics required. Message pausing allows clear tracking of the system behavior. Easy of development, write drivers in user space using POSIX standards. And it's faster development cycles and safer testing. Coming to scalability, They runs from small embedded devices to large multi-core systems. That's why it's scalable. Services scale independently without modifying the kernel. Coming to the cost, yeah, there are some system overheads to be considered. Because services run a separate process, message parsing introduces specific runtime overheads. I could put that in two different way. One could be more context switching, and second could be more copies of data. And more context switching, I mean the system calls turn into messages delivered to server process. Example, process manager or file systems. So each message involves switching to the microkernel, delivering the message, and switching to the server process, processing the request, replying back. So you have lots of context switching here. So this can cause higher context switching frequency compared to the monolithic kernels. And the second drawback is more copies of the data. When large payloads are transferred between the process, data may need to be copied across address spaces. Although QNX uses the optimizations like zero copy message passing and shared memory, still we have some overheads to look into it. Monolithic kernels can share the data directly inside the kernel space, making them slightly faster for heavy I/O operations. So thank you for the opportunity for presenting the NTO architecture. Thank you.